Nearly a third of Americans, that's around 113 million
China's
people,
largest
are
river,
currently under heat
Yangtze,
advisors.
has
Water
dried up.
temperatures in the ocean around Florida are off the charts.
Scorched millions of hectares of agricultural land, leaving thousands of Chinese citizens in need of government support.
Travel
More in
disruption
this
across
next
Europe, with
report.
dozens of flights
Rescue
cancelled to
teams
and from.
in India are searching for more than 100 people missing.
What if this is the best weather we'll experience in our lifetimes? You might have recently come across a headline like this. The Atlantic Meridional Overturning Circulation is approaching a tipping point. The AMOC is part of the world's global oceanic circulatory systems that are all being affected by climate change. This is something we've seen in historical records as well as in theory, but now from new modeling and data, we are able to see where we are headed. But before we talk about tipping points and ocean currents, let's talk about the ocean and climate. Land and water have different thermal capacities. That means water takes a lot more time and energy to heat up and have a change in temperature. And cordially, it will also take longer to release that energy back out into the environment. Opposed to that with land, which heats up a lot quicker and also releases that energy back a lot faster, which we can measure in rapid changes in temperature compared to that with water. Now, this is very key in a coastal area where the interface of land and water happens. When we take this phenomena and zoom out to a larger level, we see that large bodies of water and land heat up the air over them at different rates. This results in the phenomena such as sea breeze and land breeze. But it might make you wonder, why doesn't the water at the poles just keep getting colder and the water at the equator just keep getting warmer? Well, it actually does. And that's where ocean currents come into play. See, there are three types of ocean currents. The first is tidal currents. As the name suggests, they are driven by the tides. See, the moon is not that far away from the earth, and it is quite massive. Its own gravity pulls the earth, and the oceans, being a collective fluid, get pulled with it. This creates the level of the water to rise and fall with the combination of the gravity of the earth and the moon, and also to some degree the sun. But tides are a regular phenomena. The second type of currents that we also have are wind-driven currents. They create phenomena such as upwelling and downwelling, where water that gets pushed to or from the shore causes water from the depths to be pulled up or pushed down to the depths, creating a circular motion that can enrich coastal areas with nutrients and oxygen. On a more global scale, there are wind-driven currents that can pull water to the basins and along for thousands of kilometers. The third type of currents is thermohaline currents, and they are the primary topic of this video. As the name suggests, they are driven by the differences in density created by temperature and salinity. They're much slower than the other two currents, but they cover large tracts of our planet, resulting in this global circulatory pattern that is quite predictable and trackable. To simplify what's happening, water at the equator surface gets warmer and less saline, causing it to move towards the poles where it's colder and more saline. This causes the waters at the poles to then sink further down, where it travels along the ocean floor back towards the equator, where once again it rises up, getting warm, and continuing this cycle all the way in these chains that have now been established all along the planet. What's interesting is what happens at the poles. So when water freezes, it releases its dissolved components, including salt. So when water freezes at the poles, it releases that salt, making the water around it more dense in salt. In turn, if it melts, that fresh water adds to the ocean water around it and makes it less saline. Most of the coastlines all along the world benefit from these currents. They don't just regulate temperature, they also bring nutrients and oxygen to the coastlines all along the world. That means if these currents cease to exist or even diminish, that will impact the productivity and economies along the coastlines all around the world. Furthermore, the water that travels down carries with it carbon dioxide that it absorbed from the atmosphere. Once it reaches at a certain depth, it is able to be chemically trapped by the oceans. This is very important because currently the oceans are absorbing roughly 3 billion tons of carbon dioxide every year, and that plays a big part of the overall 10 billion tons of emissions that we have on the planet, keeping the progress of climate change kind of restrained for now. Can you hear the buffaloes? Can you hear me? So the oceans have three primary functions that are of key importance to us. The first is that they increased biological productivity, which is the fact that oceans have more life in them because of these ocean currents. Second is that they trap carbon dioxide, taking it to lower levels where it can be trapped chemically. The third is the regulation of continental temperatures. Since these currents move around on a thermohaline gradient, which includes temperature, they transport energy across the lengths and breadths of the planet. What's interesting is the new research we've had in the last couple of years. Let's start with these two papers. This here is the AABW, and this is the AMOC. These two papers used physics-based modeling on past data to study both of these currents, and what they did confirm is that yes, the currents are weakening, but also that the driving phenomena behind the weakening of these currents is the addition of fresh water. And this fresh water is coming from the melting of glaciers and poles that are being fueled by climate change. Once the researchers figured out what parameter was driving the trend in the historical data, they then used climate change scenarios to figure out what the future would look like if business continues as usual. And for that, they used the climate scenario coupled model intercomparison project phase 6, where carbon emissions for the future are taken to be business as usual, with no efforts to reduce. And their models show that by 2050, the AABW and the AMOC will slow down by 42% and 19% respectively. Next, I have this paper here that modeled the AMOC under the same climate scenario and specifically confirmed that the AMOC is headed toward its tipping point. And this tipping point is something that has been theorized in the past. It's a tipping point where the ocean currents, having been diluted and weakened to a state, will then enter a different phase where they're much slower and much less effective at providing the same benefits that they do today. Of course, if this trend continues even on, they can cease altogether, but that scenario is so far ahead and so extreme in the climate landscape that we don't really have to worry about that. But we still do have to worry about the slowing of the currents, and that happens at a threshold, which we called the tipping point. But these are just models. Models are good at simplifying reality, at pulling out different trends and different properties and studying them in isolation, confirming and quantifying how much of an effect they have in whatever system you're studying. But they don't really confirm reality. And this paper did. By studying the oxygen content in these currents, they also confirmed that yes, the AABW is weakening. As to what happens in the future, it's very hard to say. I mean, you might have seen this headline. Now, this headline is based on a paper that puts a statistical analysis on the trend of data that we have since 2004, and it extrapolates it into the future. Now, it does create a range, of course, that the Gulf Stream component of the AMOC will collapse or reach its tipping point somewhere between 2025 and 2095. Now that is a very big range, and the fact that 2025 is at the lower end of the distribution makes it quite unlikely that next year the weather is going to drastically change. But it does mean that we will be in an era where we shouldn't be surprised if it does, because that's where we are headed. And by 2095, we most certainly would have lost the Gulf Stream if things progress as they have been. Because the future, on the other hand, has a lot of variables. See, one of the things these currents do is also shield the polar ice caps. Because the water is colder and it circulates, particularly in the case of the AABW, it is also preventing warm water from making direct contact with the ice shelf. But if the current slows down and weakens, does it provide the same protection? What if it creates a positive feedback loop where the current weakens, exposes warmer waters to the ice cap, and then that causes more melting, further weakening the current, creating this positive feedback loop? What if one of these melting glaciers releases an unprecedented amount of methane that really takes global warming to a level that we didn't even model before? All of these scenarios we can't really know for certain, but what we can know is the direction we're headed by looking back at where we came from. So what can we do about it? Well, the ocean currents being the way they are, the scale at which they exist, it's really impossible to engineer anything as a solution. And as for a solution to the whole system, well, it's climate change. And we can't really do anything immediately, but this information does bring more detail and resolution to this other faculty, another system of this planet that is being affected by climate change, and which will, at some point or another, have an adverse effect on all of us. So it's another thing to keep an eye on and monitor and study, and also create some gravitas on the urgency that climate change really should be tackled now, or even yesterday, than tomorrow, because it only gets worse from here. Remember how the oceans are taking up carbon dioxide? Well, it also has a secondary side effect to the oceans themselves. See, just like the soda and what it does to my teeth, carbon dioxide, when it reacts with water, forms a weak acid called carbonic acid that makes it slightly lower in pH and reactive with calcium. So the same thing is slowly but surely happening to the oceans, and which is another side effect of climate change that, if we don't address, will have devastating impacts on marine life. All these goats.
Yeah.